Good morning, good afternoon, good evening, everyone. This is Shan Liu from Tencent. It is my great pleasure to have this opportunity to give this talk today. The title of today's talk is Learned Visual Data Compression Technologies and Standards. Today's talk will include three parts. In part one, I will give an overview about learning-based visual data compression, which includes learning-based image compression, learning-based video compression, and learning-based volumetric visual data compression, such as learning-based point cloud compression. In part two, I will introduce some recent and ongoing standard activities on learning-based visual data compression. For example, in JPEG AI, in JVET, neural network-based visual coding, and in IEEE future video coding. In the last but not the least, I'd like to bring up some discussion and mention some work which may not be exactly learning-based visual data compression, but are related to the subject. Okay, let's start from the first part, overview of learning-based visual data compression, in which we will first take a look at learning-based image compression. Before we dive into learning-based image compression, let's first quickly look at conventional or non-learning-based image compression framework. In traditional compression, an image is first converted from spatial domain to frequency domain by applying an invertible transform such as DCT, and then in the frequency domain, the coefficients may be quantized to reduce the bit usage. After that, the quantized coefficients are encoded using entropy coding methods such as Huffman coding or arithmetic coding to form the compressed bitstream. At the decoder side, first the entropy decoder decodes the bitstream to obtain coefficients, and if the coefficients are quantized, then we perform inverse quantization. After that, the coefficients are inverse transformed to reconstruct the compressed image. The figure in this slide presents an example JPEG image encoder followed by the corresponding decoder. JPEG uses DCT transform with Huffman coding, and JPEG 2000, the later generation, uses the wavelet transform with arithmetic coding. JPEG is the first widely adopted image compression codec, and after that, the last about 20 years, maybe longer, there have been more image compression technologies developed to enhance compression efficiency and quality, such as the angular interrupt prediction scheme used in H.264 AVC, and later we also developed H.265 HEVC still image profiles. Deep learning has demonstrated its super capability of solving computer vision and image processing problems in the last decade. And witnessing such success, researchers and engineers are motivated to investigate learning-based technologies for image and video compression. In fact, some researchers started exploring the utilization of neural networks for image compression as early as in 1990s. However, the computing power back then could not afford training and solving complex models. Hence, the compression results did not seem very promising. In recent years, with the advent of greater and cheaper computing power, the huge amount and also a huge amount of training data, learning-based image and video coding tools have regained a lot of research interests. If we look at the stages or types of learning-based image compression methods, we could probably put them into three categories. First is learning-assisted image compression, where we use learning-based pre- and post-processing methods such as super resolution and filtering to enhance quality or save bits. And the second category is the hybrid learning-based image compression, where the conventional image compression framework is used, but some or all of the components are replaced by learning-based methods. And the third one is the end-to-end learning-based image compression, in which the backbone of the image compression system is learning-based or neural network. Nowadays, when we say learning-based image compression, we usually talk about the end-to-end scheme, which is also the focus of today's talk. So this is a basic framework for end-to-end learned image compression, borrowed from Ballett's 2017 SELR paper, which is frequently referenced since it was published. Here, the X is the input image, which goes through the analysis network to generate Y, the latent representation, and the latent representation represents the information of the image in another domain. It is then quantized and encoded into the bit stream. On the decoder side, the quantized Y or Y hat is decoded from the bit stream and sent to the synthesis network to generate the reconstructed image X hat. As we know that in compression, there is always a trade-off between saving the bit usage and preserving the compression quality. Here, a loss function is designed as rate plus lambda times the distortion to combine the impact from both bit rate and distortion, and the training is conducted using the loss function from end to end in order to find the best trade-off. A few popular learning-based image compression methods or frameworks have been developed and published on top of the basic framework just introduced. The framework on the left was presented in ICR 2018, which could be seen as an extension of Ballett's 2017 SELR work. The left side shows an image autoencoder architecture where the analysis and synthesis transforms are convolutional neural networks. Q represents quantization, and AE and AD represent arithmetic encoder and arithmetic decoder, respectively. Then the right side adds a hyperprior, which contains transforms H analysis and H synthesis. H analysis transforms Y to the hyperprior Z, and Z is then quantized and compressed using the factorized model. Then H synthesis transforms the quantized Z or Z hat and outputs sigma, which has the same dimension as Y or Y hat. Although the hyperprior Z takes some bits to compress, Y can be more efficiently compressed with the help from Z, and thus the overall compression could be more efficient. The three images on the left bottom of the page visualizes the latent Y in the factorized and hyperprior models. The left image is the original image. The middle image presents the visualization of the latent representation Y of that image learned by a factorized model. As we can see that there is clearly visible structure around edges and textured regions, indicating that some dependency still exists, which is not captured by the factorized prior. The right image represents latent Y divided element-wise by their standard deviation. As can be seen, this reduces the apparent structure, indicating that the structure is captured by the new prior. Later in the same year, the same group of researchers from Google published a work in which they further added an auto-regressive prior on top of the hyper, which is shown in the block diagram on the right. The proposed model jointly optimized an auto-regressive component that predicts latents from their causal context, along with the hyperprior and the underlying autoencoder. This slide shows the results in objective measurements to compare the methods just introduced with some known non-learning-based benchmarks such as JPEG 2000, and MPEG. The left figure shows that both hyperprior and context models, if used by themselves, could outperform JPEG and JPEG 2000. The combined approach has the best rate distortion performance. Then, according to the authors, this was the first learning-based method that outperformed BPG on PSNR. And the right graph compares the relative performance of different versions of the proposed method. It shows that using a hyperprior is better than using context-only approach, and that, of course, combine both yields the best RD performance. In the previous a few slides, I have introduced a few of the most known learning-based image compression frameworks. In fact, there are quite some research about learning-based image compression in recent about 5 years, such as the RNN-based, GAN-based, etc. And due to the time limit, I will not go through those work. Instead, here's a list of papers that you may find to read if you are interested. Next, I will give an overview about learning-based compression on another or more comprehensive type of visual data, video. As we know that a video is a sequence of still images along the time axis, therefore video compression techniques may be largely put into two categories, inter-picture compression techniques and intra-picture compression techniques. During the past 3 decades, many companies and research institutions around the world have invested a lot of resources in the development of several generations of video compression technologies, and some of them were used to form several generations of video coding standards, such as the well-known MPEG-2, H.264 AVC, H.265 HEVC, H.266 VVC, AV1, etc. And this slide presents an example HEVC encoder. As we can see that a video encoder is much more complex than an image encoder. Same for the decoder. They presented HEVC encoder diagram in this slide was published 9 years ago, and the newest video coding standard VVC, which was just finalized last year, is more complex than this one. So the fact that conventional or non-learning based video compression is more complex than image compression also indicates that learning-based video compression could be more challenging than learning-based image compression. Generally speaking, research works on learning-based video compression could also be classified into 3 kinds. In the first approach, neural networks are applied to some components, for example, intra-prediction, in-loop filtering, etc., in the conventional framework, and the training or optimization is done locally or components on some specific components. And in the second approach, although the conventional framework is used, key components are replaced by neural networks, and the training is performed from end to end. And the third one is the autoencoder approach. Recently, the second approach, which performs the end-to-end training based on conventional framework, has gained a lot of research interest and delivered some promising results. I will introduce some recent published work along this line in the next a few slides. This slide shows the work presented in Lu's 2019 CVPR paper DVC. The block diagram on the left-hand side is a simplified illustration of the predictive coding architecture used by a conventional video codecs such as H.264 and H.265. The proposed end-to-end video compression network is shown on the right. As we can see, this work adopted the conventional video compression framework at the same time, utilized neural networks for its powerful nonlinear capability. Learning-based optical flow estimation is used to obtain the motion information in replacement of the traditional block-based motion estimation. And a motion compensation net is used for frame reconstruction. And two autoencoders are used to compress the motion and residue. All the modules are jointly learned through a single loss function to achieve the trade-off between reducing bit usage and improving or preserving compressed video quality. According to the authors, this is the first end-to-end video compression deep model that jointly optimizes all the components for video compression. This slide compares the compression performance of DVC with conventional codecs H.264 and H.265. The results are sourced from Lu's 2019 CVPR paper. According to the paper, the proposed method outperforms H.264 when measured by both PSNR and MS-SSIM. It also achieves a similar or better compression performance when compared with H.265 in terms of MS-SSIM. The authors used FFmpeg very fast mode to generate H.264 and H.265 compressed bit streams for those experiments. We know that some other presets could result in better compression performance, and also H.264 and H.265 encoders they used are probably not optimized for mean square errors, but are probably optimized for mean square errors, but not MS-SSIM, and thus the comparison or claim may not be entirely fair, especially for the MS-SSIM case. But having said that, this work has good values as it demonstrated a direction and possibility that end-to-end learned video compression may catch up or eventually outperform conventional video compression methods. Learned video compression is relatively a new research area, and most progress has been made quite recently. Here, I listed some of recently published and widely referenced papers. The first one was just introduced. Following that, a few pieces of work along the line which perform end-to-end learned compression on conventional video coding framework were published last year. As we mentioned at the beginning of this section, video compression consists of intra-frame compression and inter-frame compression. Some of these works use conventional methods such as BPG for intra-frame compression, while Most others use learned image compression methods for intra-frame compression. And the focus for video compression, different to image compression, is how to estimate or learn and compress and then use the motion information. Two popular networks for learning motion information are FlowNet and SpyNet, and an autoencoder is typically used to compress the motion information or the flow map. A composition net or a refinement network or their variations are typically used to form a higher quality temporal predictor, and residue frames are generated by subtracting the predictors from the original frames and then compressed by learning-based image compression methods. And reference 1 to 5 only apply to unidirectional temporal prediction and composition or P-frame compression, while reference 6 proposed an end-to-end learned framework for bidirectional or B-frame compression, and reference 7 presented an autoencoder approach. In the next few slides, I will briefly go through these works in high level. Resolution Adaptive Flow Coding, or RaFC, framework was presented in CVPR 2020, in which motion information or the flow maps are estimated or learned and compressed in multiple resolutions rather than in single resolution as done in other or previous works. The proposed RaFC is used both at frame level and block level to cope with different motion patterns, both globally and locally. Frame level RaFC is used to automatically decide the optical flow map resolution for each video frame, and the block level one can select the optimal resolution for each 64 by 64 macro block. In addition, the rate distortion criterion is applied to both RaFC frame level and block level to select the optimal motion coding mode to achieve higher coding efficiency. On a high level, this work shares the spirit of block adaptive motion composition in conventional video compression. And the figure on the top right visualizes the reconstructed optical flow map of one frame picture and the selected motion or flow resolution block by block by using the proposed RaFC block method. It can be observed that the smaller the blocks, the smaller size blocks are often preferred by areas around the moving object boundaries, while the larger size blocks or lower resolution flow maps are preferred in the smoother areas. And this slide shows some experimental results of the proposed RaFC compared with H.264, H.265, and DVC. The results demonstrated that RaFC outperformed DVC in all cases. While the previous works used one reference frame for inter-frame prediction, a paper presented in CVPR 2020 proposed to utilize multiple reference frames for inter-frame prediction, which is referred as M-LVC. This slide compares the framework of the proposed multi-reference frame architecture on the right with the framework of DVC as the benchmark on the left. The blue highlighted networks in the proposed system are new, while other networks are the same as those in DVC. with a note that in the proposed framework, the autoencoder, which was used to compress motion vectors in DVC, is now used to compress the motion vector difference in the proposed M-LVC. The motion vector difference is generated with the new network called multi-scale aligned MVP, and this multi-scaled aligned MVP AMVP net uses multiple reference frames to help generating the motion vector predictors, which are then used as input to the motion vector refinement network. And two refinement networks, MV refinement network and residue refinement network, are introduced to compensate for the compression error from the autoencoders. And the motion compensation network also takes the advantage of using multiple reference frames. All the modules in this proposed scheme are jointly optimized through a single rate distortion loss function. This slide shows some results of the proposed M-LVC framework compared with previous work, DVC and H.265 and H.264. It can be seen that the proposed M-LVC framework outperforms DVC in all cases by taking advantage of using multiple reference pictures. And the chart on the right compares compression performance when using different numbers of reference frames. It is not surprising to see that the more reference frames used, the better compression performance may be achieved. Here DVC uses one reference frame, and the proposed curve was generated with four reference frames. When the number of reference frames reaches to 3 and above, it seems that the additional compression benefit becomes limited. As mentioned earlier, motion estimation or flow estimation is very important in video compression. Most work on learned video compression, including the ones just introduced, use one of the popular networks, FlowNet or SpyNet, to generate the flow map. These networks, especially the FlowNet, has been there for a while and are handy for people to use. However, they have some known limitations, such as they cannot handle fast motion well. In last year's CVPR, the scale space flow network was presented, in which a generalized warping operator was designed to better handle common failure cases such as fast motion, and thus can provide competitive compression results. I will skip the details of this paper due to the time limit. The reference is listed at the bottom of the page for your interest. The several frameworks just introduced only support unidirectional or P-frame prediction, whereas we know that bidirectional or B-frame prediction can usually bring quite noticeable compression gain. A paper in CVPR 2020 proposed a hierarchical learned video compression, also noted as H-LVC method, which allows compression across 3 hierarchical quality layers. As illustrated in the top left figure, the frames in layer 1, 2, and 3 are compressed with the highest, medium, and lowest quality respectively. And the first layer, marked by red frames in the figure, is encoded by image compression, still image compression method, similar to the iframes in traditional codecs. The frames in layer 1 consume the highest bit rate, and have the highest compression quality. As they are not predicted from other frames, they are able to stop error propagation during video coding and transmission as well. More importantly, these frames provide high quality reference to layer 2 and 3 frames and thus benefit the compression in overall. The frames of layer 2, the orange frames in the figure, are in the middle, positioned in the middle of two layer 1 frames. A new network called bidirectional deep compression network was proposed to compress layer 2 frames. The proposed BDDC network takes the previous and upcoming compressed frames from layer 1 as bidirectional references. And the layer 2 frames are compressed in medium quality, which provide fairly good reference for layer 3 frame compression without costing a significant amount of bits. The proposed BDDC network is illustrated in the bottom left of in the figure in the bottom left of the page. The remaining frames belong to layer 3, the yellow frames in the figure, which are compressed with the lowest quality and contribute the least amount of bits. In the latest deep video compression approaches, such as the ones just introduced earlier, each frame requires at least one motion map for motion compensation. However, the motions between continuous frames are correlated, and thus encoding one motion map for each frame may lead to redundancy. Hence, a new network called Single Motion Deep Compression SMDC network is proposed in this paper, which uses one motion map to carry the motion information for multiple frames, for more than one frame. And therefore, the bit rate can be further reduced. The proposed SMDC network is illustrated in the bottom right figure. And because of the high correlation among video frames, a refinement network was proposed to enhance the reconstructed frame quality by reasonably leveraging multi-frame information. Since this refinement step does not need to consume any bit, it especially works well on low quality or low bitrate frames. The proposed weighted current quality enhancement network is illustrated in the top half of this slide. And finally, experimental results show on the bottom half of this page show that the proposed HLVC approach outperforms the DVC as well as H.265. Note that the low delay P very fast mode of X265 was used to generate the H.265 RD curves here for both PSNR and MS-SSIM metrics according to the paper. Finally, I'd like to mention an autoencoder approach presented in ICCV 2019. And this paper presented a deep model for lossy video compression, which consists of a three-dimensional autoencoder with a discrete latent space and an autoregressive prior used for encoding. Experimental results from the paper also showed that in high bit rate range, the proposed method can achieve MS-SSIM score close to H.264 and H.265. Besides image and video, there are other types of visual data or visual data formats such as point cloud, mesh, light field, etc. And recently there have been some work to apply learning-based technologies to point cloud data compression.
The basic framework for learning-based point cloud compression is similar to what is used in learning-based image compression. And on top of the basic framework, some improvements could be made in various aspects to help improving the compression performance, such as pre and post processing, enhanced entropy coding models with hyperprior, etc. Because point cloud signals are in 3 dimensions, and therefore 3D convolution and deconvolution are used in point cloud compression instead of 2D convolution as used in image compression. And in most previous works, 3D voxels are used to replace 2D image pixels in the neural network-based point cloud compression. A different approach was proposed by Yan and his colleagues in 2019, which directly fed 3D points into the autoencoder instead of using voxels. According to the authors, this is the first autoencoder-based geometry compression codec that directly takes point clouds as input rather than voxel grids or a collection of images. All right, by now I have given an overview of learning-based technologies and some recent works applied to image, video, and point cloud compression. And meanwhile, some standard organizations such as the well-known MPEG and JPEG and ITU have also started looking into the possibility of standardizing learning-based compression. Next, I will give a brief introduction about some recent and ongoing standard activities on this subject. First, let's take a look at standardization of learned image compression under JPEG. JPEG, the Joint Photographic Experts Group, is a joint committee between ISO, IEC, and ITU-T. During the past several decades, JPEG has produced a series of image coding standards, such as the well-known and widely used JPEG, JPEG 2000, JPEG XR, and a few more. A couple of years ago, JPEG committee created the learning-based image coding adult group, JPEG AI, which aims to develop image coding solutions following an end-to-end learning-based coding approach, potentially towards the definition of a standard. It is worthwhile to emphasize that JPEG AI primarily focus on autoencoder type of solutions as opposed to learning-based tools or components in conventional coding architecture. This page provides the history and timeline of JPEG AI activities. As mentioned in the last page, JPEG AI issued a call for evidence in February 2020 and released the final report of that call for evidence in October. In the JPEG AI call for evidence evaluation, which was held in conjunction with MMSP 2020, each proposal was evaluated following the procedure illustrated in the flowchart on the right-hand side. Both objective and subjective qualities are measured. Objective image quality is measured by computing several quality metrics, including the well-known MS-SSIM and BMAF, and a few more. And for subjective quality evaluation, the double stimulus impairment scale methodology was used. The JPEG AI database was constructed for training, validation, and testing the proposed learning-based image coding solutions. In JPEG AI CFE, the proponents were allowed to use a different training dataset provided that it was fully described in the proposal. And the test data set was only for evaluation of the final performance of the learning-based image coding solutions, and were not allowed to be used for either training or validation. In fact, the test images were kept hidden during the CFE preparation to avoid being used for training. This slide shows the objective results of JPEG AI CFE using several objective quality metrics, including MSSSIM, VMAF, and a few more. And this slide shows the subjective results of JPEG AI CFE. Just briefly showing for information. And this slide provides some information about JPEG AI, its mandates, contact information, etc. for your reference. If you're interested in their activities, you may subscribe to their email reflector and join the discussion. Bitrate control has been a challenging issue for learning-based coding, and many existing methods need to train an independent model for each bit rate as an individual task. To reduce the model size and speed up the inference, one method was proposed in last October's JPEG meeting, which employed a multitask network to support variable bitrate coding. The key idea of this proposed method is to allow different tasks to reuse partially shared model parameters, and the sharing follows a carefully designed microstructure so that the inference computation can be effectively reduced and the single task performance can be mostly preserved. And due to the time constraint, I will skip the details of this method, but the reference is listed at the bottom of the page if you're interested. And this slide shows the experimental results of the method just mentioned. The 2-bit rate and 3-bit rate models were tested on JPEG AI test set. Results show that by using the proposed method, the model size can be reduced about 50%, which means the size reduced to half, with only less than 1% performance drop compared with the single task model. Okay, while JPEG AI works on standardization of learning-based image compression, JVET, another standard group, is exploring the possibility of standardization of learning-based video compression. Like JVET, the Joint Video Experts Group is another joint committee between ISO-IEC and ITUT. And late last year, JVET published the H.266 VVC standard, and previously its predecessor, JCTVC, Joint Collaborative Team on Video Coding, developed the H.265 HEVC standard and extensions, and earlier JVT, Joint Video Team, developed H.264 AVC standard and extensions. This page provides the history and timeline of JVET neural network video coding activities. As we can see that the neural network-based video coding exploration under JVET can be traced back to as early as 2018, and it is still actively ongoing. And JVET neural network based video coding common test conditions are similar to the main JVET CTC, which was used for VVC development. And due to the time limit, I will refer the details to the CTC document provided at the bottom of the page. Early JVET exploration activities on neural network-based video coding used DIV2K image data set for training. But JVET understood that image database may not be ideal for training video compression models and has been actively searching for suitable video training data sets. Late last year, we identified a video dataset collected by a research group from the University of Bristol, and the group had agreed to let JVET use it for the neural network based video coding exploration activities. And in January meeting this year, another video dataset was contributed to JVET neural network-based video coding exploration in document JVET U0116, which contains 86 different sequences in 4K resolution, original resolution, and some thumbnails or snapshots from these video training datasets are shown in this page, just as examples. More video training data, both in quantity and in diversity, would definitely bring benefits to the exploration of learning-based video coding standardization. Different to conventional video coding tools, neural network-based video compression solutions are typically associated with much higher complexity in computation, such as numbers of operations, memory consumption, and bandwidth, etc. Hence, implementation complexity is an important aspect to be seriously considered in standardization, especially if the standard aims to be adopted in future products. Besides encoding and decoding runtime, JVET, a neural network-based video coding adult group, requires proponents to report some other implementation and complexity information such as a GPU, CPU type, epoch, batch size, loss function, etc., to help us better understand the complexities of the proposed networks. Techniques proposed to JVET neural network-based video coding exploration include both end-to-end coding solutions and component coding tools, such as neural network-based in-loop filters, neural network-based intra-prediction and inter-prediction, and super resolution is also included in some proposals as part of their solutions. And based on the input contributions, JVET established the exploration experiments on neural network-based video coding to investigate common interested topics. And in the meantime, the Future Video Coding Study Group under IEEE Data Compression Standards Committee has also started investigating learning-based image and video compression in around 2019. Similar to JPEG and JVET, the Future Video Coding Study Group also has its own test conditions, training, validation, and test data sets, as well as evaluation procedure. So this slide shows the FVC test conditions, and due to the time limit, I will skip the details, and you could find more information in related literature. And also you may contact me or the related standard group if you are interested in collecting more information. Okay, I have given an overview about learning-based visual data compression technologies and some ongoing standard activities. At the end of the talk, I'd like to briefly discuss about the challenge of learned visual data compression and a couple of related subjects. So in some earlier slides, we've already seen that the complexity of learned compression methods is generally much higher than the conventional methods. For example, the decoding runtime of learning-based methods is typically tens to hundreds times slower than traditional methods, and the memory size desired by neural networks is far beyond what current hardware platforms could or would like to afford, and thus there is a lack of cost-effective hardware support. And the models may also impose some limitations. For example, the networks usually perform multiple times downsampling to extract features, which impose limitation on the feasible prediction block sizes. On the other side, the traditional coding methods seem to still have room for more coding gain. In fact, during the development of VVC, some technologies were proposed but not adopted at the time. And in last JVET meeting, it was shown that by integrating those tools into the current VVC reference software, more than 10% BD rate savings could be achieved. And all these are challenges that learning-based video compression researchers might want to be aware of. There are a couple of research and standardization directions I'd like to mention, which might be related to the main topic of today. The first one is video coding for machines. According to some independent reports, the volume of video consumed by machines is exceeding the volume of video consumed by human. Hence, how to compress video for machines or machine vision tasks has become a hot topic in both academia and industry. MPEG created an adult group named VCM to study the requirements for potential of standardizing video coding for machines and related technologies in July 2019, and the CFE was issued earlier this year. Some typical machine vision tasks include object detection, segmentation, tracking, etc., which may be used in many applications such as intelligent transportation, smart city, intelligent content, and so on. The video coding for machines adult group looks at efficient compression performance, ability to support one or more machine tasks, and the ability to support multiple tasks or combined machine and human tasks in one codec. 3 possible processing pipelines were suggested for MPEG VCM activities, which are shown in this slide. Due to the time limit, I refer the details to the document listed at the bottom of the page. Another related subject is neural network compression. With the increasing need for neural networks in all the above-mentioned applications and technologies and solutions, and especially to run those networks on edge devices, high-speed and low-power inference of neural networks has become a critical point. MPEG issued a CFP for neural network compression in January 2019, aimed to reduce model size and enable model running on low-power devices. And the first part of this standardization has actually been completed a few months ago, and the second phase is still ongoing. Okay, so in conclusion, today I gave an overview of learning-based visual data compression, and then I introduced some related standard activities, followed by some discussions, and that concludes my talk, and thank you very much for your time.